let's do a coding lesson. How's everybody feeling? All right, if there's music playing, it's playing, and you'll have to mute it yourself. I don't know why Discord doesn't automatically mute that, but it's a thing. Let's get started. We're going to be covering a lesson today on abstraction. First, we're going to cover what that is, why you want to use it, and how to apply it in your code today. We're going to be here for an hour. I've got my timer. I'm going to start just to keep pace. Un aurito. Perfect. All right, so let's start with the base of the lesson. Let's get my screen share rolling. Make sure I don't dox myself. So, we've got two cubes, and we're really only going to be using this guy for now. This is what we've got rolling. We've got a cube, changes its color. It's on an infinite loop. You know, it's a very simple example. We bust the code apart. Starter variable for the asset itself. Colors relegated into a dictionary. And then we've got our loop. Now, this works, but it's a very messy solution. The reason I call it a messy solution is there's a lot of repetition going on. We've got a task that weight in between. Red, orange, yellow, green, blue, purple. It's supposed to be colors of the rainbow so we can have some RGB going on. Now, obviously, doesn't look super great. Why are my plugins opening? It doesn't look super great because it's just kind of flipping between colors. And the problem that we've got is, let's say we want to add a new color. We've got to add another task.wait. We need to add a new chain onto the table. Let's do pink. And if we want to continue to add anything else, we need to keep making these extensions. Now you could say, okay, Will Seal, I can prepare this stuff beforehand. I can get this set up with whatever changes I want to make, and then it's no biggie. Or even what we just did here, it's no big deal, right? We just added an extra key and an extra value onto our dictionary. Now I've got a fresh color. It seems simple because we've got a small block of code. This is 28 lines of code. When you're making a game, I guarantee it's going to go over 1,000 at the minimum. So, what happens if we have a bunch of these? This is our first problem. We've got all these color parts. They're working in unison. And let's say we want to add an additional color onto these. What can we do? What's the solution, I guess, that we could use to figure out this problem? I'm going to open this up to everybody else. If you've got an answer, you can use the raise hand feature, and I can throw you up on here to speak. Does anybody have any ideas? You know, we need to unify all these parts, because if we want to make a change, we got to go into each of these scripts individually and make an adjustment. Yes, Toast, get up here. Great idea. So, that actually solves two problems. See, this guy's all smart. That solves the issue of all of them basically needing to apply changes at the same time, but that also removes having to have a unique script in each part. Now, you could easily say, well, what's the problem with just having a script in each of these parts? You know, what's the big deal? Sure, it's 28 lines of code, but that's really not that bad. What's the problem? Well, how this works under the hood in the engine, Roblox Studio, is each script basically has to create a virtual machine. Maybe you've messed with that if you use Apple and you want to run Windows. It needs to create a virtual machine or a fake computer to execute the code. The reason it needs to do that is because this engine is actually programmed in C++, and these Lua scripts are being ran off of a virtual machine that basically the engine itself is interacting with in C++. That's where things like task.wait come from, is this is actually a C++ function being translated from Lua. So, each time we have a script created, we get a new virtual machine. So, we get a new virtual machine, and it's creating a fresh thread for each script. Thread is basically the reader that reads from left to right, top to bottom. And all of these threads get started when our place immediately starts. When I hit this run button, we get a new thread and a new virtual machine, the same frame that I hit that button on each of these color cubes. Now, that's not a big deal right now, but in a game, when are you only going to have, I don't know, whatever, 20-something assets that use code? You've got a game that's like Anime Dungeon Fighting Simulator, and you've got hundreds of thousands of weapons, enemies, maps, different assets that use code. Each of them have a unique script. Then all these scripts, all these threads, all these virtual machines need to be created when you hit the run button. What you'll find is as your project gets bigger and bigger, your initial load time actually starts taking longer and longer for before the game to actually run. You'll basically be staring at that blank skybox for a longer period of time when you run a test. That is multiplied by 100 when you're on a mobile phone. So that could be a reason why your game's performance is starting to suffer if you're noticing that issue, is lots of scripts. So, like Toast brought out, if we stick it all in a folder, well, check it out. We can delete all these, just have our one little guy over here. Let's create a folder. Oops, let's not push the right mouse button. Let's create a folder. Call it cubes, and we'll throw our cube in there. And if we go out to server script service, instead of looping through just one cube, we can go through the folder. Now, there is another issue we're finding. Let's say we were to convert this into the folder. Let's grab our folder here. It's workspace.cubes. We'll grab the children. We'll throw it in a loop. Cube in pairs. All these guys get stuffed in here, and instead of part, we're just going to roll with cube. We still have to do this for each individual color. So if we have this go down our list, orange, yellow, green, this helps fix the problem of publishing code, but that doesn't fix our performance issue. Because now, for each color, it's got a loop. Say we've got 4 of these. Through each one of these, adjust the color. This is all happening in a single frame. So we're talking, less than 1/100th of a second. And then, waits, repeats. The more cubes we have, the more the game is going to start to lag. It'll actually get to the points where either the script will crash from performance timeout, or we'll actually start seeing them change color in a row, not simultaneously. So, what can we do to fix this problem? Well, we already started a little bit with sticking it in a folder and just using a script instead of specifically typing script.parent. What I'm talking about is the principle of abstraction. Abstraction, we can think of it like paintings, is basically like comparing a Rembrandt and a Picasso. Those of you that aren't art nerds and actually know what that is, Rembrandt was a very famous painter in the Renaissance era that did these beautiful portraits. Very realistic, lots of detail. Pablo Picasso, on the other hand, did abstract paintings. Basically paintings that, to a certain point, didn't even look like real life. They were whimsical, they were melody. It looked like you were on acid staring at his painting. But basically, the principle here is that you can have specifics, good, detailed paintings, like a Rembrandt, or you could have an abstract painting, something that is more of a concept rather than a physical thing you can see, touch, hear, and feel. Here's how we apply that to the script. Let's give an example. Workspace.cubes.part. Do we know what this is? Like, let's say if we stick this in a variable. My first part. Well, of course we do. It's workspace.cubes.part. So now we know if we're ever going to change or edit my first part, we're specifically changing this cube right here. That's like a Rembrandt painting. It's specific. We know exactly what we're changing. We're simply executing a command. We're having the computer execute a command. What about our loop over here? Well, we know what this is. This is the children of cubes right here in Workspace. But what's cube? See, that's a little more different. This is more like an abstract painting. We don't actually know what cube is. Let's say that we create a bunch of these. We make a couple. There, we've got 6 cubes. It could be this part, 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 any number of these. We know that cube is at least going to be a child in this folder, one of Cube's children, but we don't know which one. In fact, if we were to stick more things in this folder, we might not even know if cube is an actual part. That's an abstract concept. That's abstraction at work. Instead of a specified command, we instead have a set of instructions with data that needs to be input. Basically creating this divide between logic and data. Let's use a different example to kind of break this apart. Let me position my camera a little better. I've got a GUI here. Now, what I want to create is a very common type of interface you see in video games. A page system. Let's say we're making a shop and we've got displayed right here in the center the item that our player wants to buy. We give them arrows that let them flip to different items. By clicking, it simply moves to different items. How do we go about making a system like this? Well, I've got our main here. Let's pretend that this represents our item of sale. Each time I want to push these arrows, the right arrow is going to increase what item we're looking at, and the left arrow is going to decrease what item I'm looking at. Here's our local script. Now, we could just simply bind it so that when we use the left or right buttons, it adds or subtracts one number off of our number here. That would work. The problem is that would be taking advantage of the fact that this is a test. This is essentially an example. If we were to replace the number that we're changing with a page that needs to be set to either visible or invisible, suddenly that wouldn't work. So let's do this instead. We could keep it simple. Let's create some functions here. Left.activated connect function. Right.activated connect function. If you notice, I'm using activated instead of mouse button one click. The reason you use activated is activated works with the mouse, the controller, and mobile phones. So if you want to have an interface that can work on mobile, you got to have this too. Mouse is only going to be looking for the specific mouse input. So we've got left and we've got right bound. We've got our main here, which has our text. We could keep it super simple and just, when they push it, if the number's 1, display page 1. If it's 2, display page 2. Maybe if we want to create some pages in here, let me grab a frame. We could just display these, but watch what happens. We do left, we say if main.text equals 1, then page store. Let me make this a little realistic, you know, for making a game and you've got interface designers, they're going to be terrible with naming things. Player list and leaderboard. Crazy names, we can't rely on the names. So if the text is 1 and it's left, we're subtracting. So we'll just say, you know, at the end, main.text equals 4. That's our maximum here. We'll say script.parent.page.visible equals false. Script.parent.page.not page. Leaderboard.visible equals true. Maybe this will look familiar. Let's grab an else if dot text equals 2 and dot text equals 1, so on and so forth. We just keep adding these here. This is eventually going to start to resemble a mountain if you just look at the code and you look at the ridges. Dot store, so on and so forth. This is basically just going to turn into this never-ending chain of ifs and else ifs. It's going to creep its way down. And then for right, we got to do the same thing. We got to keep creeping farther and farther down. So we're stuck in the same situation as the color cube. How do we manage these specifics without actually being specific? Well, I know we've jumped a couple examples, but to basically teach us the lesson of splitting logic in data, we're going to play a game called FizzBuzz. So, we'll hop back to this in a minute. We'll put a pin in this. After we solve FizzBuzz, we'll go back to our local script and then finish our color cubes. What is FizzBuzz? FizzBuzz is a game that a lot of people learn in school. Basically, you count to 100, and if the number you're saying is divisible by 3, you say fizz. If the number is divisible by 5, you say buzz. Otherwise, you say the number. If it's divisible by both, like the number 15, you're going to say fizz buzz. So it would go like 1, 2, fizz, 4, buzz, so on and so forth. Once we hit the number 15, we got to see fizz buzz, and then we know that our code's essentially going to work to 100. So let's kind of work our way through this problem. For I equals 1, 100, do print I. All right, we're starting by printing our number. We already have that done. Before we print I, though, we can say if I modulus 3 equals 0, then modulus is going to tell us essentially the remainder if these are divided. So if I divide I by 3 and it's the number 15, modulus is going to return 0. There's no remainder. So with the modulus, we can tell if things evenly divide. Print fizz. Else if I modulo 5 equals 0, then print buzz. Let's check both, else if 3 and 5. Then print fizzbuzz. Otherwise, our last else, print I. And so this will work. This will play fizzbuzz nicely if I open up the output here and I hit run. Let's check our work. 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, fizz. I should have checked this first, and then 3. Fizz, buzz. Always works until you try to teach it and then it doesn't. equals 3, then print fizz. All right, let me hit run and give this a shot. And here we can see 15, we've got fizzbuzz. But we're still stuck in that same problem. If I want to add 7 in here and have it print baz, we need to add an if statement for each unique number. Then we got to check their combinations. And basically, we get this unmanageable format of code that just needs to continuously grow exponentially, right? It literally multiplies the amount of work we need to do each time we add something on until it becomes unmanageable. So the solution to fizzbuzz, and one of the reasons why this is such a good game to play when you're learning to code, in fact, this is actually a very common interview question at different major companies when they're basically vetting programmers, is this teaches abstraction. What we need to do is we need to take out all of our data, 3, 5, fizz, buzz, fizzbuzz. This is all data. We need to strip our data and only write logic. So right now this has no data. We've got numbers like 1, numbers like 100, but the rest is we've got I, we've got our print. So by basically putting a handicap that we're not allowed to specify what things are, it allows us to do much more powerful things with our code. Maybe let's write some generic logic like local string equals get string. If string equals nothing, then string equals I. We'll finish our loop off by printing string. There we have it. That's our loop. We'll throw I in there just so we can pass it as an argument, but basically, once we format this function, we can accomplish what we had in those if statements just off of this. We've got an empty variable that calls a function. The function gets an input, which is our data, I, and it will output the string that we need to print. We check if the string's empty. If it's not, set it to our data, print string. Now we just have one if statement. We don't have this ever-increasing chain. Now you could pipe in and say, okay, well, Seal, you actually haven't wrote the logic. This is a cop-out. This is just a function that you're assuming is going to do it without expanding if statements. But let's see what we can do to basically not have to use if statements to format our string. So what we'll need to do is use a dictionary. We've got our number. What we can use, because dictionaries allow us to input data without having to specify what it is, we could just throw a variable in. It basically allows us to use number to dictate what we have. So for instance, we've got number is 3, the value is fizz. I forgot an equal sign. Let's do another one. We have a dictionary in an array. Number is 5, value is buzz. And now all we got to do is loop through this table. For I equals 1, strings do local file is strings by index, and then we can say if file, actually in fact we could just do if file dot number equals number, then let's flip this to a reverse to create a gate. Continue skips the loop, so we'll head down below. Continue would just cause it to move on to the next one. We will grab string our value here, and we'll combine them. We'll say string equals string concatenated with file.value. And so now with these, we basically have a loop that's going to go through this table. It's going to check the number to number. If it's the same, it'll grab the value here, fizz, and it'll attach it to our blank string. At the end of the loop, we'll return our blank string. Now, the reason that this will work specifically for 15 is because we're combining values. Now, if you've got numbers like 3 and 7 or 3 and 5, it'll just grab fizz. Get out of here, code assistant. And it'll grab Baz. Let's give this a shot. Let's see if we can get this working. All right, we've got no strings. What's going on? Okay, so our string is coming back blank. Ah, well, this is fun. File.number does not equal number. Continue. Otherwise, string is string. Let's check file and you know what I forgot to do? I forgot to actually divide these numbers. I am a dummy. Does not equal 0. Oh man, well that was fun. And it's still not even working. Number 0. Oh, I got it backwards. Oh, thank goodness. Okay, and there is 15 Fizzbuzz. We've got Fizzbaz. Oh, man, that was a mess. So, now that I actually didn't forget the division here, we've basically solved our problem. Anytime we want to add on to this argument, add a new number, add a new string, all we got to do is just add a new dictionary piece here. That's one line of code with some slight changes. And we'll basically just keep increasing this little list here rather than having exponential growth with if statements. Instead, we basically have two if statements. If we want to get rid of this if statement, we could say string equals getString and not blank and I. And that would get rid of our thing there. String does not equal I. Or actually, I'm sorry, we would need to do a second line down here. String equals, string does not equal blank I, or, yeah, string. And so now with this little ganky, whatever, dank variable assign, we can basically limit this entire piece of logic down to one if statement. Now, the principle behind this that we've been talking about, data and logic, is if you look at this, like if you were to read this code, basically this whole thing, if you were to ignore the specifics of value and number, along with the 100 here, you would have no idea what we're adjusting. We don't know what number is. We don't know what value is. We don't know what string is going to turn into. We're instead writing the set of instructions that go along with this. And so let's take this principle. Let's go back to our local script and see if we can find a way to basically convert these pages without needing to have these exponential if statements. I'll give you a hint. It's tables. Pages. Throw them in here. Let's hop on our local script. Let's assign this to a function. Local function change page. We'll create a argument for our metric. Change page -1. Change page regular 1. So now we either have 1 or we've got -1. let's create a counter. Base starts at 1. Counter is going to reflect main's text. So we'll start by saying counter plus equals metric. If you add a negative number onto basically just a flat positive number, it's going to reduce, even if you're using plus. So now this basically allows us to update the page. Main.text equals toString counter. With this piece of logic here, we can now adjust our page. Let's say we basically add wrapping here by basically turning this folder into an array. We'll say local pages equals GUI.pages get children. Now if we want to change the page, we'll say if counter is less than 1, then counter equals the end of pages. Else if counter is greater than pages, yes, I caught that, greater than pages, then counter equals 1. Let's check if this works. 2, 3, 4, 1, 2, 3, 4, and now we've got basically page wrapping. 2, 1, 4. Okay, perfect. Now we can use counter, since our change page function lets it start from the base to the end, and we'll use counter to basically cycle through our list here. If you're doing that item display store that I talked about earlier, basically you could just have an array of the item data, including the model, and write a generic function that loads the page. Like, we take this one here, load page, we'll need a new variable. Current page is nothing. We'll change the page, and then we'll load the page. We can pass counter in, we'll call it page number. So we'll say if current page, then current page.visible equals false. Then we can say current page equals pages page number, current page.visible equals true. Now if I want to go through here and mess with the colors, we can actually tell these apart. We can test our code works. And voila. Now we've got smooth page scrolling. It wraps between. And guess what? We look at our code. What do we want to do? What do we need to do if we want to add a new page onto this? Well, all we got to do is go down here, create a new page, change the color so we can actually tell it apart, and our code compensates. Now, slot number 5 is this fresh page. Isn't that awesome? We didn't have to change a single thing to our code. It actually just adapted to what we have in our folder. Let's add a ton of these. Now we've got all these pages, and our code just works with it. Now, this is cool for displaying the page, but we do have another issue. Like with our cube example, what do we do if we need code to run with these pages? Like, let's say we open up the leaderboard and it suddenly needs to build itself with the players. We switch to player list, it needs to construct who's on it. We switch to store, it needs to load the assets and set up the click detections for actually buying in-game game passes. What do we do if we need code to be unpacked? Well, that basically adds a little extra layer of complexity. We could keep it simple and throw a script in there and just enable the script when we call load page, but we'd be right back to square one with our cubes having tons and tons of scripts being created every time we want to add something new. Well, basically what we can do is, again, using dictionaries and sneaky functions with arguments, we can compensate for that. So instead of adding a fresh script, we just add in the behavior that needs to go with the data that we're passing. Dictionaries allow us to basically specify data. Like with FizzBuzz, we can specify the string right here. We can specify the number, the value, the behavior to go along with it without having to define what it is in our logic. We don't have to specifically say strings spot number 2 or, the word buzz, the number 7. Instead, we're just using variables. So let's apply that now instead of our page counter. Let's apply that to our color cubes. We've got full circle. Back into control, we're already in one script. Let's instead convert this into something a little smoother. Let's go through here and write some fresh functions. We'll say a local function, change color. We have to provide the color that we're giving, which will be cube and color. Cube.color equals color. Now we've got a really simple function that'll change the color. So instead of this, we'll just say change color, cube, colors.red. Okay, well that's a step in the right direction. Let's abstract this further. Let's pull this out into smaller pieces. Let's get rid of this. We're having to specify which color we're passing in. Instead, let's turn this from a dictionary into an array and create a counter like with our GUI. And that also lets us get rid of all the extra lines in here. Colors, count, and when we're done, we'll just say count plus equals 1. Let's not stick it in there, let's stick it outside. And this will basically fix our problem where our color cubes are still working. I forgot to make that repeat. 1 second. If count equals colors, then count equals 1. There we are. So now we've got colors that'll cycle, and we're basically not having to call this same loop over and over and over again for each of these. Let's see if we can abstract this a little further. So we've got our count that basically removes the need to have a bunch of these for loops line after line. Instead, we can keep it pretty simple and just top to bottom. But what if we want to add complexity to this? Take our RGB. Right now it's kind of flipping between colors, but if you look at your PC or you look at your keyboard or some other RGB thing you got going on, it's smooth. It's got all these little colors in between that it's displaying, instead of just flipping from color to color and probably giving someone a seizure somewhere. Let's change that. Let's disable our control. Let's go into our color cube, which has our most basic script, and let's add on to our complexity here. To change colors smoothly, like if you want to make a rainbow thing, we're going to need to use tween service. Tween service. Now, if we're going to format this like a code or like a script that's readable, that basically you can work with others and collaborate on, we got to use some basic formatting principles. First one, no magic numbers. This is a magic number. If we create a tween that's got a tween time, that would be a magic number. A magic number is basically something that appears in your code and you're not quite sure what it's for. Like 0.25. One's pretty cut and dry. You know this is a counter. It starts from 1, it climbs. We add 1 or we start from the base. But our time isn't. So we would just add what's called a constant. A constant, you're going to type in full caps with underscores separating words. That's so you know it's a constant. Constants should not be changed throughout your code. A constant is a given thing. It shouldn't be adjusted. We've got our color chart. So that means we shouldn't edit the colors in here, and we should never change this time. If you intend to change the time here, don't make it a constant. All right, so this is coming together. It's making some changes. Let's throw this in a local function. Loop colors. So loop colors is going to go through our cubes and apply a color. So I should probably change that to apply color. Cubes. And now we'll just change cubes. So this will go through, it'll change the color of the cube using color chart count. We'll pass that in as an argument. Let's go down here to our loop. We'll say task.defer, so we stick this in a custom thread. While true do, we have our count here. And we'll say apply color. We'll do cube. Let's maybe do cube folder over here. Cube folder. Workspace.cubes. So we've got cube folder and we've got count. Now we also have this little logic in here that we're messing with the counter. Now this is in our main loop, so maybe we can abstract this further and stick it in a function. Local function, progress. Number limit. Number plus equals 1 if number is greater than limit, then number equals 1. Return number. And so now all we have to do is just say count equals progress count color chart. So now we've got these smaller functions that basically do one thing. The functions themselves don't actually know what they're adjusting. So change color doesn't know what cube is, it doesn't know what color is. Progress doesn't know what the number is, it doesn't know what the limit is, it just knows how to find if it's past the limit. Apply color, even calls color change color. The only spot that knows what our data really is basically our highest level function, the one that's actually running the loop. And so this is how we build sort of a structure or a hierarchy. A hierarchy is this here. Textures inside a base plates inside a workspace. A hierarchy of power, parent and child next to each other. We do the same with our functions. The lower the function gets in the chain, the less it knows. The higher the function gets in the chain, the more it knows. This is the highest level function. It's only called by us, the programmer. Therefore, it knows the most. Even the highest level function doesn't quite know what it's doing. It knows what count is. It knows that it's infinitely looping. It's going to wait for a specified amount of time that it doesn't know. It's going to apply a color from a folder that it doesn't quite know. With a count, it doesn't really know what it is. And it's going to progress this abstract number. The benefit of structuring our code like this is now anytime you want to change the wait time, what the folder is, or the colors, you essentially have a little list of settings that you're adjusting. You never have to go in here and tweak the code. You don't need to go through this super long script and find every time you said task.wait and adjust the number you threw in there. Instead, they're all using a uniformed time right here. Let's go into change color now and add our tween. More constants. Let's get our info. Tween info.new. Let's have this tween wait time. The rest will be fine. If you leave it empty, the default easing style is going to be linear, which is just basic. That's fine. To go in here to change color, we'll just say local new tween equals tween service create. We've got our instance, which is cube, our info, which is tween info, and our property table, which is going to be color equals color. We'll say new tween play, and we'll return new tween dot completed. Now, what we'll do is this is going to loop through, and it's going to play all of these tweens. If we want to essentially save one of these in the future and have something wait, all we need to do is, just call change color wait. This would actually yield until the color's done. That's useful for other stuff. But now we're basically going to go through and tween all these cubes instead of sharply changing the color. Let's make sure I didn't make any mistakes. Already made one. Table expected, got instance. That was my problem. Cube folder, get children. There we are. And now we've got fully functioning RGB cubes. Those look pretty good. Want to adjust the time? Let's say it goes a little faster. All we got to do is mess with this little time up here. Lengthen it, increase. Let's go through and create a bunch of these. Now, we've got a ton of color cubes that move in tandem. They're all using the same script, and they're all using the same thread. Now, of course, if we want to increase the amount of cubes to an extreme degree, we are going to need to start multi-threading. And that leaves us with another problem of, okay, how do we keep track of the threads per cubes? How do we make a new one per? But for now, we've got a ton of cubes. We're still bound to data, though. Let's see if we can abstract this further. We're stuck with this. What if somebody goes in here, one of our builders, and they mess with the name of the cubes folder? As the kids would say, we're cooked. Basically our code breaks and we have to go back in and fix it, adjust the new name, yada yada. Let's do something different. Let's get rid of this. And let's treat each cube as an abstract instance. What we can do is we can utilize Roblox's tag service. If I go through all these cubes, and I mark these with a tag, and I call this color cube, these all now have the tag color cube, I can go in here and use collection service to treat these as unique classes or unique objects. Collection service. And now we need to say for in iPairs collection service get tagged. Let's make a new constant. Our tag name do. And this will loop through every object that's been tagged as a color cube. We have got an error, and I don't know where it's at. Huh. Ah, there it is. Cube. We don't need the index, but we need the cube. Now we can go through and we can say task.defer, apply color. We can clear this and just use change color. for our cube. Cube, color chart, count. And so now we're creating a unique loop, and we'll say while cube dot parent, while cube exists, do. If cube gets deleted, this loop will break because cube will no longer have a parent. Then what we can do is add a quick extra thing. We'll bind this in a function for that. Set RGB. Perfect. We'll go down here and add a check that basically runs when instances are created. Instance added signal. Tag name. Connect. Cube. Set RGB cube. And so the benefit of doing it like this with tags is, check this out. Let's run this. Okay, so they're all running, and they all have their unique loop. So if I create a bunch of these, right, we're not going to start having lag because they're on basically separate threads. We make this mass amount of color cubes. And now all I need to do for these is if I want these to start behaving like a color part, all I got to do is give them the tag. Let's go there and let's say tags, color cube. And there they go. Now they're acting as color cubes. Basically in a game, if you want to spawn a car, for instance, and you want to run something off of a tag called car, all you got to do is throw the model in the workspace and then just tag it as a car. And suddenly the behavior that you've defined, in this case we defined the behavior color cube, gets applied to the data that you're sending it to. That's kind of the theme here, separating data in logic. Aside from our constants, so let me snatch these. Now, with how we have this structured, aside from our constants, this has 0 data. From line 17 down to line 59, we don't specify what anything is. This is all pure logic. None of this is data. The data now is relegated to this little section of settings that we can easily adjust right here at the top, and our code is able to just perform the set behaviors without needing any adjustments. That's kind of the theme. Learn to code behaviors instead of commands. Basically, instead of writing scripts with specified things that your code needs to do, oh, change the part's name to this, adjust this right wheel down here to turn at, whatever said speed. Instead, we're just defining, this is the behavior of a color cube. This is the behavior of a car. With our interface, this is the behavior of a page, of a turning button, of our counter. We define the behavior and then provide what needs to follow that behavior. Because of coding this way, we could take our local script. We could use this local script on all the different GUIs in our game that need to function like this without actually needing to specify. We could literally tag this as a turn page interface, and it's going to look for our 2 buttons and our pages folder. We could create a ton of these. Different vehicle stores, we could use pet stores, we could use any type of page system in our game, dialog boxes, whatever. Give it a tag, and our code works. Our single script, we don't have to go find it, make adjustments. It's just there, and it behaves. Now, there is an issue here with this type of system. You may have noticed this is very simple code. I didn't code a car. I didn't make a leaderboard, a player list, a store that each need to have their own complex system to control. I made a very simple page turning system, a very simple RGB cube system. These are all very basic. We're manipulating numbers, we're manipulating strings, we're making stuff visible. We're not interacting with other things in the game. How do we fix that problem? Well, if the behavior is advanced, the bigger and bigger the complexity gets, the larger our script will get that follows, and it gets much harder to manage and it starts getting messier. We start needing to be able, we basically need to be able to separate behaviors into small little boxes and make them super reusable. That's very difficult to do with scripts because we can't use set RGB outside of this. We can't use this progress function. We've got that right here. Progress, this is really useful. A number and a limit, and it wraps. We could actually use that for our local script in here. That's essentially what change page does. The problem is, again, we can't reuse these from different scripts. So that's kind of our two issues. How do they communicate? How do we reuse stuff more? And how do we extend complexity without increased size, increased mess, right? Well, we need to adopt a way of thinking that's breaking things down into classes, components, and services. Classes would be like Color Cube. Color Cube is a class. Color Cube is a set of behavior for an object that we're defining as Color Cube. Components would be things like our progress, or in our local script, our left button, our right button. This is a page button. It changes a number and it loads a page. This is a component that would go into our class, our turn page menu. Now, to be able to allow this communication, we need to basically get into object-oriented programming. That's a way of using metatables and tables to create classes and components while having services oversee, create, and manage these classes and components. Tags give us a start. Tags makes it helpful. But to actually be able to create a class, we need to delve into how metatables work, and we need to delve into how tables themselves work on the back end level. How the engine Roblox Studio handles basically tables. So, that is the theme for our next webinar. This one's going to end right here. That's the end of our lecture, Abstraction. And we're going to break into basically how we create classes. If you're interested in checking out how to see that, I've got a page on my website on webinars. I'll post it. You can get more information there.